Yeah, so good morning everyone to the class back on tribology. So there was some technical snack, so sorry for the delay in starting. And in the last class, if we remember, we were dealing with related to the delamination theory. What is its importance and how an laminated film comes out during the delamination concept. So later we dealt about the delamination theory. After that, we dealt about the summarization of the steps which are followed in delamination theory. So after doing this, then we came straight away to understand how the wear happens in case of metals, right? So we learned about when the friction and wear will be more and when it will be less with respect to the adhesion behavior between the metal and its alloys, right? And later we dealt about different wear coefficient values for the metals which are paired together and for mating elements with unsimilar metals. So we analyzed how the wear coefficient will reduce when it is of unsimilar metals. So when you mate two similar metals, the wear coefficient will be extremely high. That shows that it has very less resistance to wear. So it is always preferable to go for the mating components of dissimilar metals. And we dealt related to its hardness number as well. So this was being dealt in the last class, and later we studied the wear map behavior for soft carbon steels. So we analyzed here taking the sliding velocity along x-axis and the pressure along the y-axis. So we dealt how the region changes from plastic wear to severe plastic wear, so which is the transition region. So below this you will be having a very mild wear, right? So once it crosses the velocity of 1 meter second, the oxidation phase starts. And after that oxidation phase, you can get the phase of severe oxidation wear. So as the pressure increases, it can reach the phase of melting also. Above all these protocols, above the pressure of 10 to the power of -1, if you have any kind of high pressure, then it results in sudden damage where it will be a total scrap, and that is due to the Seuser. So this wear concept we analyzed for soft carbon steels. This kind of wear map could be analyzed for any kind of mating component what you are using. So based on the wear map, one can understand which is the feasible region, comfortable region within which you can apply the load, and which is the nominal sliding velocity that you can apply, so that it helps for the component to run and get the required efficiency with reduced amount of wear. So like this you can analyze for all other metal components as well. So this was the thing what we dealt in the last class. And now we were supposed to start up to understand the concept of wear in case of ceramics. One thing, even during the time of friction, related to metals and non-metals, we discussed that in metals you will be having the metallic bonding between the two components, whereas in case of ceramic the bonding is mainly due to the ionic or covalent type of bonding. So that bonding concept also you should understand. So with this simple background, let us start up with the wear of ceramics. So here you can see always the ceramic materials differ from metals. Why? It is due to the nature of interatomic bonding. I told you here it is mainly due to the ionic or the covalent bonding. Whereas in case of metal, it is direct metal bonding which takes place, right? So this is one thing, the difference which comes with respect to the metal. And as a result, this leads to a very limited capacity for plastic flow at room temperature. Due to this, the plastic flow at room temperature will be comparatively limited in comparison to that of the metals. Okay, so next point in comparison to metal is, in compared to the metals, ceramics are more inclined with respect to time respond to a stress which has been subjected. So mainly it gets a failure due to brittle fracture. Okay, So this is the difference. In case of ceramics, if any crack penetrates, it is totally a brittle fracture, which comes into picture, and it responds with respect to the time factor for the stress applied. So this is the second concept what you have to understand. And in case of ceramics or any oxides of ceramics, if you are using, right? So then the crack growth, which is initiated across the contact, is very sensitive to the environmental factors. Okay, so this due to this reason, what happens is it affects the mobility of the wear surface dislocation. Anyhow, the ceramics are subjected to the various factors when it is kept in open atmosphere, and secondly, along with that, when you have the crack growth, it is also sensitive to the environmental factors, and it badly affects the mobility of the wear surface across the dislocation. So this dislocation again comes across the contact area, right? And hence this is also influenced by the plastic flow. So such type of effect which is associated with chemomechanical effect is known as ray binder effect. So if they ask you what is ray binder effect, it is the effect which is caused due to chemical and mechanical combination, because mechanical effect is subjected to the ceramics due to the applied load or the pressure at the contact area, but with respect to environment it is also very insensitive to it. So due to that, certain chemical reaction also come across the contact area, right? And it results in mobility of the wear surface also across the dislocation. So this combination of chemical cum mechanical effect in case of ceramics across the contact area is known as ray binder effect. So this you have to understand. The terminologies, let it be very clear. Okay. So suppose if you have the ceramic mechanochemical, if you have ceramic components and if it is unlubricated and it is sliding, then what happens? It usually results in significant tangential forces. So due to the tangential forces, in case of ceramics, it leads to fracture than that of the plastic flow. You know what you mean by plastic deformation, that we understood already in case of our wear terminologies analysis, right? So all those aspects. So this plastic flow is nothing but about the deformation what they are speaking. So rather than that of plastic flow, here the ceramic is subjected to wear mainly due to fracture, because ceramics are of brittle in nature. So this helps in easily leading to fracture than that of plastic deformation. So this is the main difference between the wear in ceramics to that of wear of metal. So where it easily leads to fracture, not for plastic deformation. In case of metal, it easily leads to plastic deformation rather than going for fracture. Why? Because it again depends upon the nature of the material what you are selecting. Here in case of ceramic, this is brittle in nature and hence it leads to fracture. And one more concept what you have to understand is sliding wear mechanism in ceramics can mainly involve fracture. That is the first thing usually what it happens. Next are tribochemical effects and plastic flow. So in wear mechanism, related to sliding wear mechanism associated with ceramic mechanic components, it is always like, usually what type of wear it comes into picture is first is fracture. Apart from fracture, tribochemical effects can come into picture because it is sensitive to environmental factors, and lastly about the plastic deformation. So usually come across wear categories are these three. And the next point what you have to understand here is the transition between the regimes dominated by each of this commonly lead to sharp changes in wear rate with load. So what do you mean by this? So there is a transition in the load applied from one region to other. So as we studied here in case of wear map, change of transition region. Similarly in case of ceramics also, so there will be change in the region. regions. So this is mainly dominated, the change of transition is mainly dominated depending upon what is the sliding speed you're applying or what is the amount of load you are subjecting, and the sliding speed is also affected by the environmental condition. So based on the environmental condition with respect to the sliding speed, the wear rate will vary with respect to the pressure which has been applied. So depending upon the wear rate, the transition also will be affected, right? You know the range, this is the range, the safer range. So if you have a sliding velocity less than 10 to the power of minus 2 meter per second, and if the pressure applied is very less of 10 to the power of minus 5, then the amount of wear what you get is very mild and it is within the safe zone. So by reading this map, you can know the range in what you can apply. Similarly, it is spoken here in case of ceramics, right? So based on the sliding speed, what you apply, and based on the load, with respect to environmental condition, the wear rate will be designed. So depending upon the wear rate, the transition region also changes. And this transition region is mainly dominated by these parameters: the wear rate associated with the load applied and the sliding speed associated with the environmental condition. So one should play very safely with respect to the sliding speed and the load, so that the amount of wear which is coming in or creeping in into the ceramic mechanical components will be reduced and it will be within the safe zone. So these are the parameters one has to think about if you are designing the mechanical components made up of ceramics. And apart from that, there are a few things what you have to understand. Then we'll explain these concepts related to one of the ceramic component, right, in the next graph. And also I told you mild wear is associated with low wear rate. As in the diagram here, the mild wear is associated with low wear rate, right? Similarly, in case of ceramics also, the mild wear is always associated with the least wear rate. And usually at that surface, what happens is the surface will be smooth and you won't be having many wear debris into it. So as the wear debris increases, the surface will not be smooth enough. There will be some asperities and it results in the formation of friction, and the mechanism of different type of wears comes into picture, and these are dominated with respect to tribochemical reactions or the plastic deformations. So these all comes into picture when the wear rate is more. Only when the mild wear is there, it is associated with the low wear rate. At that case, the surface is smooth. But as the wear rate increases, the asperities across the surface increases. It makes the surface not smooth. It results in the formation of rough surface across the contact area. So this results in accumulation of the wear debris. Once the wear debris are accumulated, it helps in enhancing the traces of friction, and also it results in dominating the different type of mechanism of wear which can creep in. So due to wear, what happens is it results in either the plastic deformation or with the tribochemical reactions across the contact area, and that makes the material to be scrapped out. So this is a difference what you have to explain when the wear rate is less and the wear rate is more. So similarly, these concepts are now explained in the diagram here shown. Okay, so this is just an diagram which represents the coefficient of friction and wear rate as a function of sliding velocity. Here the sliding velocity is taken along the x-axis and you have the wear rate and the coefficient of friction which is taken along our y-axis. So these are the results which are taken out for silicon nitrate. So when the silicon nitrate is hot pressed, so it could be hot pressed by using some hydrothermal process, yeah, whatsoever, by subjecting a normal load of 10 Newton at an ambient atmosphere. Okay, so this was evaluated very long before in the year 1985, right? So for the material silicon nitrate, so when the silicon nitrate was compressed, hot pressed by hydrothermal process with a load of 10 Newton. This was the results which was being evaluated, right? So you can see the two graphs here. So this dotted line is towards the coefficient of friction, and the continuous line here, what is been drawn with the direction towards your left, shows the values for the wear rate. So what happens here basically is you can observe with the sliding speed, the coefficient of friction is also increasing. Sorry, this is the graph. With the increase in sliding speed, the coefficient of friction gradually increases, but it is not enhanced in the initial state. So that shows that this is the so until it is around 100 plus meter, 100 plus per second, right? The coefficient of friction was gradually increasing. So once it crossed this value of sliding speed towards 1000 per second, we could see that there was a rapid enhancement in the coefficient of friction. So that means to say that if you set the sliding velocity below 100, then you can have a mild coefficient of friction. So that shows that if the coefficient of friction is little bit lesser, even the wear rate across the contact area will be comparatively less. So this was about the coefficient of friction value for silicon nitride when it is hot pressed with a load of 10 Newton. So we can say the safe, if you look at this graph, we can identify the safest sliding speed for silicon nitride. So it has to be below 100. So it has to be below 100. It has to be below 100 per second to see that the coefficient of friction is the least. So above 100 per second, it gradually enhances. Similarly, now you have to come for the wear rate. So what happens in case of wear rate? Here you can see that this is again the sliding speed. So the wear rate here is plotted along the y-axis. So this is the graph what we have to understand. So until it is 100 100 plus per second was the sliding speed, the wear rate was almost negligible, means it is nearly very less value. So this is the safe zone of the sliding speed. So once it crossed 100 per second, then the wear rate increased rapidly, and it even reached around 6 into 10 to the power of minus 6 cube per Newton meter. So this was the wear rate. So if you plot the wear rate and the coefficient of friction for a particular material when it is performed experimentally, you can see that which is the safest sliding speed for the components to be slided against each other. So if that safer sliding speed is identified either theoretically or experimentally, then it is always better to run at the same safe zone of sliding speed so that the coefficient of friction which comes into picture and the wear amount will be within the safer zone, so that you can run that component for a longer extent until and unless is needed to be slided and to get the required result. So you should be able to check out the properties of the material, identify which is the safe sliding speed. So with respect to safe sliding speed, what is the amount of wear rate you're getting and what is the value of coefficient of friction. So if you're able to analyze and set a table with respect to these values for each and every material in the database, then it will be like you will be having some confidence. Okay, so this material, this is the highest sliding speed what I can give for, wherein the wear rate and the coefficient of friction will be very less. So if I cross the sliding speed at any cost of time, then the wear rate will shoot up, coefficient of friction shoot up. So I should be always safe to stick on below the sliding speed only. So this concept will be there in your background so that you can design the material and operate it as per the required parameters. Then you can say that the component is reliable until its life cycle because you are following the safe zone parameters related to that particular material. So this funda or the concept can apply at a good constant, not only for ceramics, even for other metals also. So this is how you have to look and put forward your concept before designing any mechanical component. All of you are mechanical engineers. You know what is material is, you know how to design. So any product what you want to manufacture, you should be knowing thorough knowledge about the material properties, right? So then you can design accordingly and select the best material with the right properties, with these parameters of sliding speed, the pressure, the load applied, all these, so that you can make the component reliable with reduced wear and tear and friction concepts. So this is how, as a tribologist, one has to think, design and select the material and finally manufacture it. So where the wear will be at the least, because the wear rate within the safer zone will be the least value. I hope this is clear, guys. Hello? Yeah. Similarly, there is one more concept what you have to understand here. So here you can see a graph where we have taken relative humidity along the x-axis and the wear rate along the y-axis. So this is the graph what we are analyzing for the same material, silicon nitrate. So silicon nitrate here is sliding against itself. Means to say both the mechanical components, the mating point, the mating element is also the same. So silicon nitrate versus silicon nitrate, you have two mechanical components which are sliding against each other. Okay. And this sliding against itself in a pin on disc test. Okay, so we have studied different sliding mechanisms, right? So it is the category which falls into pin on disc test. So you'll be having a disc and a pin will be pivoted, that will be held stationary and the disc will be revolving. So it was slided with the help of pin on disc test parameter in air, means in open atmosphere. So when it is subjected to open atmosphere, humidity comes into picture. And I told that all ceramics usually are affected by the external surrounding environment. So when it is subjected to open atmosphere, not in any inert gas or vacuum chamber, it also affects the wear. So how it affects the wear, you can just see the graph and observe. So what's happening here? So relative humidity, and this is the wear rate. So the wear rate will be the, so you can see here the wear rate, the values given here are from 10 to the power of minus 8 to 10 to the power of minus 11. And here the relative humidity is in the percentage values right from 20 to 100%. So when the humidity value is nearly to 50%, you can see that this is the transition range where you can say that within this is a transition range. So once from this transition range, if the humidity is around 60%, 80%, yeah, 100%, you have the mild wear. That shows the mild values. So when the humidity is of around 20% or 40%, you can see that the amount of wear which is coming into is severely high. So also, apart from the sliding parameters, you all should also be careful related to the relative humidity in the open atmosphere. So even though you have set all these sliding parameters as per the requirement and you have mild wear rate and you have mild coefficient of friction, if the given component is badly affected by the open atmosphere due to its humidity factor, again the wear rate can shoot out. So if you have to reduce the wear rate, you have to think with respect to the external environment where it is subjected, whether it is kept in open atmosphere. If there is a problem persisting due to open atmosphere, it is always better to keep it in a controlled environmental condition or in vacuum chamber if needed. If the ceramic is very delicate to many external parameters, then you might think about in keeping in some inert atmosphere, okay, with the help of some inert gases. That happens in very rare cases. So these are the things even one has to think about if you are provided to design a mechanical component with reduced amount of wear and friction. Okay, so all these things you have to keep it in mind. So this was about the wear concepts which can come in related to the ceramics. So we have dealt wear of metals and wear of ceramics after delamination theory. So the last part related to the wear is now you should understand the concepts for wear of polymers. So what happens here in case of wear of polymers, right? So even polymers are non-metals. It is not metals. It comes into the category of non-metals where you have ceramics as well as the polymers. When we say polymers, we dealt about the polymers even during the friction. So we studied wear related to polymers as well as we studied friction related to polymers also. So when we say polymers, usually the things which comes into mind are like polymers could be any isocyanide, elastomers, or any plastic materials, right? So generally, these polymers shows a very low friction in comparison to our metals and ceramic pair. Okay, so it will usually show the least we can say or the low friction. It has a friction value, but when you compare with metals and ceramics, the value of it is least. But the amount of wear it shows is moderate. It is not low, right? Even though the friction is lower in comparison to metal and ceramics, the wear which comes into picture in case of polymers are of moderate range. So in case of polymers, the dominant wear mechanisms which usually comes into are the adhesive type of wear, the abrasive and the fatigue wear. We studied different wear mechanisms, around 10 wear mechanisms we studied, how it could be prevented with respect to mechanical perspective and the lubricant also we dealt about. So out of those 10 wear mechanisms, the most dominant one which comes in case of polymers are adhesive type of wear, abrasive and the fatigue wear. And in this one, what you have to consider is if the mating surface is smooth, usually the wear which comes into picture is based on the adhesive wear. So adhesive wear occurs in case of the mating surface when it is very smooth. So for the cases of, again we are speaking about the polymers which are sliding against each other. So for the cases of sliding polymers against rough surface, you know that the wear which comes into picture is related to abrasive mechanism. You know the difference between abrasive and adhesive, right? So depending upon the surface, again the type of wear what we get will get varied. So you should be aware when an adhesive type of wear comes and when an abrasive type of wear comes. And the fatigue mechanism. So fatigue mechanism is also an important thing which comes into picture when you are using hard polymers, okay, such as thermosetting polymers which are sliding against smooth surface. So when you have thermosetting polymers which are sliding against a smooth surface, the usual type of wear which comes into picture is the fatigue type. So these are the three major type which comes and dominant in case of polymers that you have to keep in mind. Okay. So asperity deformation in polymers is mainly elastic. I told you the asperity deformation takes place at elastic as well as the plastic deformation. So we were dealing related to the plastic flow in ceramics, which is not much higher in comparison to that of metal. Similarly, in case of polymers, the deformation which comes into picture in polymers is mainly of elastic in nature. So it is elastic deformation which comes into picture in case of polymers. And wear which comes into picture is mainly due to the fatigue. Okay, and this is caused due to the formation of cracks. And these cracks are always associated with elastic deformation and not the plastic deformation. This is only the main difference what you have to consider. So when you speak about polymers, it is only due to elastic deformation. Whatever the wear or the crack which comes into picture is due to the elastic deformation. Mainly the crack penetration is mainly due to the elastic deformation and wear is usually due to the fatigue. Okay, that results due to the formation of crack, and that crack is again due to the elastic deformation. So this thing you have to keep it in mind. And as usual in case of other parameters, here also crack propagation and subsequent intersection of the cracks will lead for the formation of the wear particles. So even here the initiation of the crack growth and the propagation and intersection of these cracks mainly helps in formation of wear parameters, wear particles basically. So these are the few things what you have to know. So first thing is in polymers, it could be any polyol, yeah, isocyanide, yeah, any elastomers, which will always show low friction in comparison to metal and ceramics. But the wear will be moderately high, and wear is due to three important parameters: adhesive, abrasive, and fatigue. And thirdly, the deformation which comes into picture due to asperities are mainly due to elastic deformation. This thing you have to keep in mind. And the propagation of the crack and intersection of the crack will help in providing the wear particles. So with this thing, you have to just understand a small graph with an example as we did for other metals and ceramics. So here you have speed along x-axis and the wear rate along the y-axis. So this graph shows you the variation of the steady rate of an wear with respect to the sliding speed. So it was taken for nylon. Okay. So this nylon was sliding against a smooth mild steel counter. So you had two different mating element. One was nylon of grade 6.6. It was slided against a smooth surface made up of mild steel. Okay. So here, and the main thing what you have to understand was it was unlubricated. There was no lubricated layer in between to form as an adhesive layer or lubricant film. So it was slided against each other, right, with the two different mechanical components. And here you could observe that the wear rate was almost consistent until the speed of the sliding velocity was 10 meter per second. So once 10 meter per second was crossed, right, so you had an enhancement in the wear rate. Why? Now here it shows the effect of temperature also. So here they show that even the temperature has been enhanced. So when the temperature was enhanced, it helped in increasing the wear rate. So that shows that even every material will be having a consistency in the wear rate at the room temperature. But when you enhance it for heat treatment at external high temperature, even though it was consistent, it results in shooting up of the wear rate because it depends upon the melting point of the polymer, yeah, ceramic, yeah, metal, whatever using, right? So based on that, even the wear rate enhances when it is not operated at room temperature. So this thing you have to keep in mind. So this was like computed and tested in the year 1979 by Evans and Lancaster. So this is also a data taken from a journal paper which shows you the comparison strategies with respect to the temperature, the speed as well as the wear rate. So this shows you a full picture related to the difference in wear which come across in metals, in ceramics as well as polymers. So basically, to tell you frankly, in polymers, the amount of friction is almost the least in comparison to that of what we say the metals and ceramics, wherein the wear will not be the least, it will be the moderate, and it enhances more when it is subjected to high temperatures. So these are the things what you have to understand. And there is a last part in our module 2. It is related to the standards what we have to refer in reducing the wear, which can come across in any metal or non-metal. Okay, so this we will be dealing up in the last class. This is a very small concept. I hardly have 3 slides here. So if we complete, we can, but it is 9:25. I need to take the attendance. I'll cover this and we'll start up with the third module in the next class. So if you have any doubts, kindly let me know. And the assignments are posted. See that you will complete the assignments on time, and marks are being shared for you all in the Google Classroom. Right? You have to still write better. Some have written better. Some have to improve their writing skills. Some students' handwriting is still need to be fine tuned. Okay, so please take care of all these aspects so that you can get good marks in next internals. So now everyone type your name and USN in the chat room, and please answer the attendance in the meantime. Akhil KV. Akhil KV. Akhil KV. Anil Kumar.
Present, ma'am.
Ankesh Aman.
Yes, ma'am.
Gautam Krishna.
Yes, ma'am.
Balaji VR. Balaji VR absent. Beldar Mohammed.
Present, ma'am.
Chaitanya SR.
Present, ma'am.
Chetan Kumar.
Present, ma'am.
Dheeraj CN.
Present, ma'am.
Ishant. Ishant. Ishant is absent. He was there in the morning. Harshit S.
Ma'am is
Present,
present.
ma'am.
Yeah, I didn't answer. Okay, I have marked him. Arshit.
Present, ma'am.
Himanka.
Yes, ma'am.
Kanishka. I don't know, he's absent consistently. Just ask him to call me up. Nagamurli Krishna. Nagamurli Krishna. Kunal Raj.
Present, ma'am.
Danush. Absent. Mohammad Ayan. Mohammad Ayan. Absent. Mohammad Junaid. Mohammad Junaid. Sri Prasad.
Yes, ma'am.
Niharika.
Present, ma'am.
Nihar Venkat Sai. Nihar. Absent. Nikhilar.
Yes, ma'am.
Nirab.
Yes, ma'am.
Prajwal S. Bhatt.
Present, ma'am.
Rishabh Pandey.
Present, ma'am.
Rohan Kaglakar. Absent. Roshan Yadav.
Present, ma'am.
Sumant Sagar. Absent. Sagar Dutt Mathur.
Present, ma'am.
Sagar GV.
Present, ma'am.
Sanjay Raghav. Sanjay Raghav. Absent. Shobit.
Present, ma'am.
Siddharth. Both the Siddharth are present. Siddharth B and Siddharth
Present,
Sridhar.
ma'am.
Yeah.
Yes, ma'am.
Subramanya.
Present,
Okay.
ma'am.
Tirumani Sethi Rohan. Absent. Ulas, you?
Present, ma'am.
I'm present,
You're
present.
present? Okay.
Rohan, ma'am.
Yeah, I
59.
marked it. Ullas,
Present, ma'am.
Vidyan,
Present, ma'am.
Varun. Varun is absent. Pavan,
Present, ma'am.
Danush. Danush is absent. Dhyanesh. Dhyanesh,
Ma'am, done with present, ma'am.
he is not answering. Okay. Dhyanesh Kumar is not there. Gunasagar,
Present, ma'am.
Meghanata,
Present, ma'am.
Rasik Baran,
Present, ma'am.
Shiv Krishna, Shiv Krishna, absent. Shreyas L,
Present, ma'am.
Shreyas, your attendance is very less. What's the reason for that? You have attended. This is the 4th class you are attending. You will get shortage of attendance. Please don't do this. I need a statement, your mail, the reason for your absent. Okay. Kindly do mail me the reason why you were absent. Srinivasalu.
Yes, ma'am.
Yogananda.
Present, ma'am.
Kiran.
Present, ma'am.
Ranveer Singh Chauhan. Absent. Gautam Sai.
Present, ma'am.
Okay. Abdul Kalik Pasha.
Yes, ma'am. Present, ma'am.
Yeah. Shiv Pavan. Alok. Alok is there. Okay. I have shared the quiz in the Google Classroom. Kindly do take the quiz and submit at the earliest. So until then, again in the next class, we'll just meet. So please take care and have a nice day. Bye-bye.
Ma'am, my name?
Alok, I called you. You didn't reply.
Ma'am, something's wrong with my mic.
Okay, okay. I have put your attendance now. Okay.
Ma'am, Rohan.
Okay, ma'am.
Yeah. Rohan, you... Alok, you have joined now.
No, ma'am, I've typed my name like an hour back.
Okay, okay. And who else called me now? Rohan? Someone else told me. Rohan Kaglakar. What is this USN number? ME042. Okay. I've given you the attendance, Rohan. Done. So please take care. Have a nice day. Bye-bye.